Bismillahirrahmanirrahim. The topic of my presentation is magnetic properties are reported in terms of magnetic moment. Magnetic moment is due to the spinning of charged particles or electrons. The spinning may be around the axis of electrons, which is spin moment, or around orbital axis, which is orbital moment. Magnetic moment is a combination of spin moment or spin magnetic moment, which is movement of electrons around their own axis, and orbital moment, which is movement of electron around its axis and around axis of orbit. There are few types of magnetism, that are diamagnetism, paramagnetism, paramagnetism, ferromagnetism, and antiferromagnetism. This is the figure of field s orbital. S orbital contain two electrons that have opposite spin. In mechanical terms, they orbit the nucleus in opposite direction, which means both electrons cause magnetic moment, but they have equal magnitude in opposite direction, due to which net magnetic moment of atom equals 0. These substances are called diamagnetic. This is the equation for magnetic induction. B is equal to H plus 4 pi I, where B is magnetic induction, H is external magnetic field or applied magnetic field. The value of pi is 3.14. I is magnetization. We will divide the equation by H and get the values of magnetization, which is I is equal to 1 plus 4 pi x, where x is magnetic susceptibility. There is another method to find magnetic susceptibility. When any substance is placed in a magnetic field, the field produced within the sample will be either greater or less than the applied magnetic field, depending upon whether the material is paramagnetic or diamagnetic. And the difference between applied magnetic field and induced magnetic field will be del H. Delta H is equal to B minus H naught, where B is magnetic induction and H naught is applied magnetic field. When diamagnetic material is placed in the applied magnetic field, it is weakly repelled by magnetic field, and when we place paramagnetic material, it will be attracted by magnetic field. Now 4 pi I is equal to B minus H naught, and this 4 pi I comes from more commonly the difference between applied magnetic field and induced magnetic field in the sample. By dividing the equation by H naught, we will get the value of molar magnetic susceptibility, which is equal to X is equal to K over D. Magnetic susceptibility is mostly regarded in form of molar. So molar magnetic susceptibility will equal to susceptibility into magnetic weight into molecular weight. From magnetic molar susceptibility, we will get the values of magnetic moment. We know that magnetic moment is due to the spinning of electrons. Spinning may be in their own axis or orbitals. S represents the spin moment, L represents the orbital moment, and J is for total angular moment. Mu is equal to G into J plus 1 whole to power 1 by 2, where the value of G is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J over J plus 1. Sometimes magnetic moment is due to the spin moment and orbital moment, and magnetic moment is also only due to the spin moment. By putting the values, we will get the final value of magnetic moment, which is equal to 2.84 into molar magnetic susceptibility and absolute temperature into power 1 by 2. Now we will have the types of magnetic moment. Magnetic moment have two types: orbital moment and spin moment. Orbital magnetic moment is due to the orbital angular momentum, and spin magnetic moment is due to the spin quantum number of electrons, which is plus 1 by 2 or maybe minus 1 by 2. Magnetic moment arises due to electrons mean. Experimentally, we will discuss observed magnetic moment and calculated magnetic moment. Observed magnetic moment: the sum of orbital magnetic moment and spin magnetic moment is observed magnetic moment. Observed magnetic moment is equal to orbital magnetic moment plus spin magnetic moment, and calculated magnetic moment in spin moment of any substance or system can be calculated theoretically. So such moment obtained are called calculated magnetic moment. Calculated magnetic moment is equal to only spin magnetic moment. Reasons for calculated and observed magnetic moment different. We will discuss the orbital contribution. The experiment values differ from spin only value because orbital motion also makes some contribution to the total magnetic moment values. The maximum value of magnetic moment can be represented by effective magnetic moment is equal to magnetic moment, which is sum of spin and orbital moment, which is equal to under root 4s into s plus 1 plus l into l plus 1 into b into m, where s is spin magnetic moment and l is orbital magnetic moment. The experimental value exceeds spin magnetic moment. They seldom come close to sum of spin and orbital magnetic moment. This is due to the complete or partial quenching of orbital moment. Diamagnetic effect. Even an atom with a permanent paramagnetic behavior will have a diamagnetic behavior, working in opposite to the paramagnetism when placed in a magnetic field, provided only that the atom has one or more closed shells. We know paramagnetic materials have unpaired electrons, while diamagnetic materials have paired electrons. But paramagnetic electrons also somehow show diamagnetic behavior due to the presence of a few number of paired electrons. Thus, the net paramagnetism measured is slightly less because some is cancelled out by diamagnetism. Spin moment only tell us about only number of unpaired electrons or electrons having their own magnetic properties. Unpaired electrons attracted by magnetic field called paramagnetic, or if paired electrons they does not attracted by magnetic field and known as diamagnetic. Units of magnetic moment. Unit of magnetic moment is reported as Bohr magneton. It is mathematically equal to 1 Bohr magneton is equal to Eh over 4 pi mc, where E is electronic charge, H is Planck's constant, m is mass of charge, and c is velocity of light or speed of light. Classification of magnetic substances. We will classify the magnetic substances on the behavior of substances when placed in the external magnetic field. And we will get paramagnetic substances, diamagnetic substances, ferrimagnetic substances, antiferromagnetic substances, and ferromagnetic substances. And there are some examples of these magnetic substances. We will discuss the magnetic states of matter. Any time two electrons share the same orbital, their spin quantum numbers have to be different. In other words, one electron will have spin up with magnetic moment plus 1 by 2, while other electron will have spin down, which is minus 1 by 2. And this is important when it comes to determining the total spin in an electron orbital. In order to decide whether electrons spin cancel, add their spin quantum numbers together. And when two electrons are paired together in an orbital, their total spin will be 0 because one electron will have spin up and one will have spin down. So they will have total spin 0. And electron spin is very important in determining the magnetic properties of an atom. Diamagnetic atoms are not attracted to a magnetic field, but rather are slightly repelled because they have total spin equal to 0. This diagram shows the electrons with spin up and spin down. Electrons. The spin up electron will have value of spin moment is equal to plus 1 by 2, and spin down electron will have minus 1 by 2. The spin moment is a vector quantity because it has direction as well as magnitude. This is also a diagram showing the two electrons, one with spin up and one with spin down. Movement of electrons. Now we will discuss how do electrons enter orbitals. Electrons will enter in orbitals according to Hund's law. First, electrons singly occupy orbitals and then they pair up. Here we will see how electrons enter orbitals. In first p1 orbital has only one electron which enters in first box, which is subshell of p orbital. If we see p4, we know that first 3 electrons enter 3 suborbitals with same spin, which is spin up, and the fourth one electrons enter the first box with opposite spin, spin down. In one orbital, the orientation of the two electrons are always the opposite of each other. One electron will be spin up and the other electron is spin down. If the last electron that enters is spin up, then spin moment is equal to plus 1 by 2. If the last electron that enters is spin down, then the ms is equal to minus 1 by 2. Diamagnetic substances which have all spins in pairs. Diamagnetic substances are weakly repelled by the applied magnetic field because these substances have fully filled orbitals. Magnetic moment of an electron with spin in one direction is cancelled by that of other electron with spin in opposite direction. The compounds are also diamagnetic when they contain no unpaired electrons. A diamagnetic compound has all of its electron spins paired, giving a net spin of 0. Diamagnetic compounds are also weakly repelled by a magnet. Here is the proper definition of diamagnetism in inverted commas. The substances which, when placed in a magnetic field, decrease the intensity of the magnetic field, then in vacuum, are called diamagnetic substances, and the property due to which they show this behavior is called diamagnetism. The magnetic lines of force tend to avoid such substances, and as such diamagnetic substances are repelled by magnetic field. These substances set themselves at right angle to the magnetic field. Examples of magnetic substances are as this diagram shows the diamagnetic substance placed in a magnetic field with poles north and south. The diamagnetic substance will position itself at right angle to the magnetic field. Origin of diamagnetism. If two electrons with opposite spins are paired in same orbital, the magnetic field produced by one electron is cancelled by the other electron because each of the two electrons has equal and opposite magnetic moment. Therefore, the substance having only paired electrons gives resultant magnetic moment equal to 0 and are consequently be diamagnetic. Diamagnetic materials are temperature independent and diamagnetic behavior is shown by all types of substances, even by paramagnetic substances, because paramagnetic substances have few numbers of paired electrons as well. Diamagnetism is much weaker than paramagnetism, 1 to 100 times weaker, and both act opposite to each other. It is difficult for the substances having unpaired electrons to show diamagnetism. Therefore, the substances having unpaired electrons show a net paramagnetism. For diamagnetic substances, magnetic induction is less than applied magnetic field. As P is less than 1, X will be negative, hence I is opposing H, where B is magnetic induction, H is magnetic field strength, which is applied magnetic field, P is magnetic permeability, I is intensity of magnetization, and X is magnetic susceptibility. Experiment for determining the magnetic properties of a sample. This is a very simple experiment in which first we weighed the sample without magnetic field in the absence of magnetic field, and then again we will weigh the sample when a magnetic field is applied, and it shows in the presence of magnetic field the mass of sample will be less than the mass of sample when it is weighed in the absence of magnetic field. There are some conditions. A paramagnetic sample is drawn into the field and thus appears to gain mass. Paramagnetism is a much stronger effect than is diamagnetism. When we will apply the magnetic field, the diamagnetic substances will have less or lower mass than in the absence of magnetic field, but paramagnetic substances has greater mass in the presence of magnetic field as compared to in the absence of magnetic field. In this diagram, sample A is weighed without magnetic field. In sample B, diamagnetic substance is weighed in the presence of magnetic field and has lower mass than in the absence. In diagram C, paramagnetic material has gained mass due to the presence of magnetic field. Variation of diamagnetic susceptibility with temperature. Diamagnetism is a weak fundamental property of all matter, arises due to the non-cooperative behavior of orbiting electrons when exposed to an externally applied magnetic field. Diamagnetic substances are composed of atoms which have no net magnetic moment because all the orbital shells are filled and there are no unpaired electrons. However, a negative magnetization is generated when exposed to external magnetic field and the susceptibility. Magnetic susceptibility is a ratio between the induced magnetization and the applied magnetic field. The magnetization is zero when the external magnetic field is zero. The other characteristic behavior of diamagnetic material is that the magnetic susceptibility is generally temperature independent. Well-known diamagnetic substances are quartz, calcite, and Walther. The diamagnetic materials are type 1 superconductors, which is a superconductor in its superconducting states is an example of an ideal diamagnet, as they exhibit perfect conductivity and perfect diamagnetization when cooled to very low temperatures. The superconductor repels a magnet and in turn is repelled. Such perfect diamagnetism in superconductors exhibiting the above phenomenon is called Meissner effect. Now we will discuss Meissner effect. The Meissner effect is the expulsion of a magnetic field from a superconductor during its transition to the superconducting state. This phenomenon is first discovered by German physicists Walther Meissner and Robert Ochsenfeld in 1933 by measuring the magnetic field distribution outside superconducting tin and lead samples. In this figure, the type 1 superconductor repels magnetic field, repels the magnetic field lines, and type 2 does not repel the magnetic field lines. When we increase the strength of magnetic field in type 1, they will lose their superconductivity. But this does not happen in type 2 because they do not have diamagnetic behavior. Properties of diamagnetic materials. Some important properties are when suspended in a uniform magnetic field, they set their longest axes at right angles to the field. This diagram shows diamagnetic material is placed in magnetic field lines and it will position itself as its longest axis will be at right angle to the magnetic field lines. In a non-uniform magnetic material, these substances move from stronger parts of the field to the weaker parts. For example, when diamagnetic liquid is put in a watch glass placed on the two pole pieces of an electromagnet and current is switched on, the liquid accumulates on the sides. On increasing the distance between the poles of magnet, the effect will be reversed. This diagram shows the diamagnetic liquid placed in U-shaped tube. The diamagnetic liquid in U-shaped tube will be depressed when placed between two pole pieces of an electromagnet. Next property is the lines of pores do not prefer to pass through the specimen, since the ability of a material to permit the passage of magnetic line of force through it is less. The below diagram shows the diamagnetic specimen which is placed in magnetic field, but the magnetic field line does not pass through the specimen. Such specimen cannot be easily magnetized and so their susceptibility is negative. Examples: bismuth, copper, gold, quartz, water, alcohol, air and hydrogen वगैरह. Here is the proper definition of diamagnetism. A diamagnetic is a substance that exhibits negative magnetism, usually considered by non-physicists as non-magnetic, and include water, DNA, most organic compounds such as oil and plastic, and many metals such as mercury, gold, and bismuth, superconductors. Here is the definition of Meissner effect. Magnetic field lines are excluded from a superconductor when it is below its critical temperature. Superconductor is a perfect diamagnet which repels magnetic flux when absolute temperature is less than critical temperature.